Hello everyone, my name is Rigveda. Today I am presenting DSBDA mini project Maize price forecasting using XGBoost. Agricultural markets are highly volatile and deeply affected by global weather anomalies. Traditional models often look at market trends in a vacuum, ignoring these massive environmental drivers. This project bridges this gap by merging climate science with machine learning to predict maize prices. We choose maize because it is a vital global food and industrial staple. We established three core objectives for this project. First, analyze climate correlation to isolate environmental variables and understand the exact time lag between a major climate anomaly and a subsequent price shock in the maize market. Second, optimize the ML core. Traditional models struggle with high dimensional, noisy time series data. Our primary goal was to deploy a fine tuned and advanced XGBoost regression model to capture these non-linear relationships with minimum error. Third, design a decision dashboard to translate complex machine learning weights and predictive price curves into an interactive, user friendly interface, allowing stakeholders to make fast and data driven decisions. Our data pipeline was built entirely within the Python ecosystem. Pandas and NumPy used for time series alignment, handling missing values via forward peeling, and calculating rolling window across 30 years of data. Scikit-learn utilized for data preprocessing, min-max feature, scaling, and calculating our evaluation metrics. XGBoost, the core algorithm of our project. It was selected because its gradient-boosted decision tree framework excels at handling non-linear data and natively prevents overfitting through built-in regularization. Matplotlib and Seaborn implemented to generate our diagnostic visual plots and time series trend lines. Let's walk through our technical architecture, which follows a structured data engineering lifecycle. First, data collection and pre-processing. We ingest historical maize prices alongside our climate indices. To prevent data leakage, a massive issue in time series forecasting, we implement a strict time-based split instead of a random train test split. We also engineer lag features, shifting climate data by 1 to 6 months to give our model predictive foresight. Second, exploratory data analysis. We run statistical hypothesis testing to validate feature significance. This ensures we only feed climate indices with a proven causal relationship into our model, stripping out redundant noise. Third, modeling and evaluation. During the training phase, we focus heavily on hyperparameter tuning, optimizing parameters like max depth, learning rate, and N estimators. We evaluate the model using a metric approach, MAE for absolute dollar variance, RMSE to penalize outlier errors, and R square score to check overall accuracy. Integration and feedback. The high precision outputs are fed into a database that powers our interactive Streamlit dashboard. It displays a climate commodity index gauge, indicating if current climate conditions are adverse or supportive, and a 1 month lead forecast graph. Finally, a new market data comes in monthly. The system allows for periodic pre-training to prevent model drift. Now let's dive into technical implementation of a Flask web application. The backend engine is written entirely in Python, utilizing an iterative walk-forward validation strategy to forecast maize prices. I will break down our code architecture into its core functional block. At the start of our script, we initialize a standard Flask server and configure an asynchronous backend using Matplotlib's target, which ensures our multi-panel graphs render seamlessly to a file system without throwing GUI thread error. Once the raw data set are passed into memory, we initialize our data engineering pipeline. First, we resolve disparate time series frequency by normalizing all timestamp indices into a clean, unified format. Trade attributes are grouped and aggregated by year, and missing sales are resolved using a forward fill mechanism to prevent row dropping. We initialize a siding cutoff window starting from January 1st, 2020. For every single month in our validation timescale, the model dynamically segregates all prior historical data to act as its isolated training set. Inside the validation step, we train a gradient boosting regressor parameterized with 1000 estimators, a shallow maximum depth of 5 to restrict overfitting, and a conservative learning rate of 0.03. Finally, after compiling all compiled multi-layered predictions into a unified data frame, we calculate our model's predictive scale. The application exposes a single root endpoint. When hit, it kicks off the entire analytical execution, converts our compiled pandas skill metrics table directly into a clean HTML table template, and serves it to the browser interface. Now let's examine the live front-end interface of our application, which displays the Maize price prediction performance dashboard. The web interface dynamically loads our generated multi-panel matplotlib visual analysis broken down into three crucial diagnostic plots that evaluate model accuracy over different forecasting time horizons. The first plot on the left displays a 1 month late forecast from the year 2020 through late 2025. The solid black line represents the actual historical market price of maize, while the dashed green line represents our model's prediction. As you can observe, the green prediction line tracks the actual price trends incredibly tight, successfully capturing both the massive price surge peaking in 2022 and the subsequent market correlation through 2024. Mathematically, this is validated by a stellar Pearson correlation coefficient of 0.93, which proves that for a short-term 1 month horizon, our engineered climate features and lag variables provide our model with immense predictive power. The middle bar chart illustrates how our model's performance scales over time by plotting the correlation versus lead horizon from 1 month out of 6 months. In data science, time series predictability naturally degrades the further into future you try to forecast. Our bar chart transparently demonstrates this expected phenomenon. The final line plot on the right acts as the inverse validation of our bar chart, mapping the root mean squared error versus lead horizon. As expected, the error curve starts at its lowest point of approximately $45 for 1 month lead. Because errors accumulate recursively across the 6 month forecasting window, the line scales upward linearly, topping out at an RMSE of roughly $105 at lead month 6. In summary, this dashboard proves that pairing global climate teleconnections with a gradient boosted architecture yields a highly reliable decision and support tool. It successfully provides agricultural stakeholders with quantified long term market foresight rather than simple reactive data analysis. Thank you.